grant to organize the GAN program. And it is fortunate that our department is organizing this program second time. And I am lucky that I got 2 times. This is the second time. And actually first time itself I have submitted two proposals. One is Professor Dorel's along with Professor Dorel Mihach, and another with Professor Brinde. So after that the COVID has come, and then I don't know, there is a shifting of the national coordinator from IIT Kharagpur to IIT Hyderabad, and because of that the delay was done. Finally in 2023, sometimes in March or April, they asked me to resubmit the consent from taking Professor Brende. So we have requested, and he sent the consent. After that we submitted, and around August first week we got the confirmation that your program accepted. Send the brochure for the program, as we can send the grants for the same. So they have sent the acceptance and all such things. Those who are the faculty members of Indian universities, they can also submit GAN phase 5. It is now closed, is going to open in January 2025, 1st January 2025. And most probably I am in a mood to submit another proposal jointly with some computer pupil and one with some other mathematics people. If possible, I will take some of my colleagues as well as some of my students also. One in data science and another in functional analysis, but on the applicational part, so that we can shine more. So let me introduce our welcome our Professor Bhinde. Welcome, sir, for this session.
Thank you.
Yeah. So he will speak on introduction to metrical fixed point theory and applications, what he talked yesterday. So he will continue the second part today. So Professor Biren.
Hello, good morning. Nice to see you again this day, very sunny day. In my country, I am very excited about the weather, because in my country it's -7, -8 and snow, so here is really beautiful, so we don't need hard clothes. I want to take first the opportunity of this announcement by Professor Murthy, and would like to draw your attention to a forthcoming conference. Maybe some of you can still register, I don't know. KFU PM, just a moment. There will be a conference 1 month by now in the King Fahd University of Petroleum and Minerals. And it's related to what Professor Murthy was saying. The conference is very interesting. Even the title is very suggestive, Maths Connect. And it is about mathematics and connections to other fields of research. And to this conference I'll give a talk about fixed point theory and connections to combinatorial optimization. Graph theory in general to celestial mechanics, and unfortunately I did not consider data science, but it's in astronomy. So some of you could, I'm sure, I don't know if the website of this conference is ready, but I'm sure there will be some speakers who will be involved in data science.
Yes.
For sure. So just look for this. Maths Connect is 10 to 12 December 2004. I haven't tried to look on this website if it is ready or not. So it could be very, very interesting and informative for most of you. Coming back to the topic for today, so in connection with these applications, a lot of our colleagues are making some critiques to specialists working in fixed point theory, at least in my country where we have a very strong group of research, that we do not consider a significant number of applications. So this is the main point. So you are too theoretical, too much theory, and you should consider applications. And in this respect, I would like to tell you that this is a very old polemics. I have shown you yesterday the polemic started by Fourier. Fourier is famous by Fourier series, and he was very applicative mathematician because Fourier series were introduced because of applications. And he said number theory is not important, so it's just a game, so nothing important. But these polemics about pure mathematics versus applied mathematics is very old. This is a problem that was stated and discussed in Soviet Union. During the 50s, 60s, Russia, it's a big force in mathematics. Till now, they produced very important mathematicians. And in Soviet Union, in Russia, it was this discussion. Applied mathematics is not very deep mathematics. And we are doing pure mathematics are important, and the other said, no, pure mathematics are not useful, so do not consider pure mathematics, only applied mathematics. And this discussion was very deep related to the research at that time. In the 50s or 60s, if you know, there was the first flight to the moon, the first rocket sent, and then all this research was devoted to such kind of activity. So applied mathematics was very, very important. But one academician, a Russian academician, in such a polemic, he said, okay, look, stop to do pure mathematics, and you will reach one day when you will not have what to apply if you do not produce pure mathematics. So we have to produce pure mathematics, but sometimes to show that this pure mathematics is connected, is strictly connected to some fields of applications, and if possible, we should give some applications. Now, I will speak you as an author, as a researcher, but also as an editor and as a reviewer. Now this trend is that in a paper on fixed point theory, it should be included an application. So this is the main objection of reviewers, of editors, include an application. Okay, you have a paper of 8-10 pages, theory, and if you include a serious application, you need other more 10 or 12 or 20 pages. So most of the authors are including trivial applications. So most of them are trivial. What does it mean trivial? Just so this can be applied. And sometimes it's the same kind of problem, change it a little bit. And I would like in this context to not speak about applications of fixed points to usual problems like differential equations, all kind of differential equations. Now is this new field fractional differential equations and all kind of integral equations. The approach for all these problems is very simple. As I said, we transform equivalently the original problem into an operator equation, and then we apply a fixed point, an appropriate fixed point theorem to this operator, and we establish existence and uniqueness if possible, and if possible, we indicate a method for approximating the solution, the fixed point. This is the typical applications. I would like to speak today on another kind of applications. If you are not familiar with this kind of applications, just search in any database like MathSciNet for differential equation and fixed point, and you'll find a lot of papers, and you can see how a differential equation is transformed by a green function in an integral operator equation, and the others similarly. For integral we have Volterra, Fredholm type integral equation or combination of them. So today I want to show you some application. It's a very particular application to functional equations. What is a functional equation? Okay, differential equation, fractional differential equation, integral are all functional equations. But by functional equation, we basically understand an equation which involves a function as an unknown, and we intend to find this function. Of course, differential equations are functional equations that involve the derivatives of the unknown functions. Fractional differential equations, similarly, integral equations, they involve also the integral of the unknown function. But here we have just simply G is the unknown function or mapping here because we work in a metric space X, D, Y is a Banach space, and the equation is very simple. Just find if F is given, F small is given, F capital F is given, so just find this function G such that this equation is satisfied. This equation has been studied for a long time. I have here some information. So starting with 1960, you can see this is not from Serbia, but from Bosnia-Herzegovina, former Yugoslav Republic. And, okay, even earlier, Germanescu, he's a Romanian mathematician, and he published he studied this, sorry. How can I show on the screen without moving? And also this Polish mathematician Kuczma studied the equation, Malenica, and in two papers. So very important kind of functional equation. And I was looking to this problem many years ago, maybe more than 35 years ago, when I was studying fixing points for my PhD thesis. I did my PhD thesis late because I worked in computer science for a while, and then I decided I want to do research in mathematics, and I switched from computer science to mathematics. And believe me, this was a very good decision because the temptation was to move in academia for computer science. And now, if I look back, I consider it was a good decision to switch to mathematics. Why? Because I used tools from computer science in my research in mathematics. So I took this advantage in many instances, having an algorithmic way of thinking to work in mathematics. Of course, I have this nostalgia for computer science because I worked 11 years in computer science. I did programming. At that time, programming was totally different of what is now. Maybe you didn't study at university the history of computer science, history of informatics. A computer was, roughly speaking, this room was a computer. And it has been big pieces of all kind of electronics, and the total memory of such a computer was 256K. This was the memory, then the whole memory. Now a phone has, I don't know how many giga. Yes, and at that time, the most important challenge was to work inside this small memory and to run big programs. So this was the challenge, very nice challenge. How to use the memory, the memory to work and such. And then, after a few years, this memory increased, doubled, actually to 512K. So this was a big progress, and then came this period. Now it's really incredible for people who worked at that time in computer science. And let's come back. So I was looking at this paper by Malenica. I have shown before this one. And I realized that what he is doing, he was using something which is connected to fixed point theory, but he was not aware of this. So in solving this equation, a functional equation, he considered such a function because he was working on the real line. He was considering such a function which was supposed to be continuously and strictly increasing, and with these two conditions, the three conditions, and then he used to prove that the sequence of iterates, so this is the Picard iteration, converges to B when n goes to infinity. So I observed that this property 2 is nothing else but is characteristic to what I presented you yesterday, Picard operators, which were introduced by Professor Roos. And you remember what is a Picard iteration? I'll show you here the definition for this case. So we have this function. So if we do not consider this fixed point A, so f is actually a Picard iteration, a Picard operator, sorry, on AB, because this was the intention. Just because the function was increasing, strictly increasing, just to have this situation, and it was an only fixed point here somewhere, B, not A. So this was the idea. So I noted this is a Picard operator, and I solve this equation in the case that we don't work on the real line, but in a general case of a metric space X and Y, the space where we work for this iteration is a Banach space, and I published this paper, an old paper of mine, on the solution of a functional equation using Picard mappings, which was published in this prestigious journal in 1990. This was one paper on functional, maybe my first paper on functional equations at this level. Maybe I should tell you that in Romania we have, in this journal I mentioned yesterday, beautiful journal. This created thousands of high-class mathematicians in Romania. Thousands. Any generation produces this, because this journal contains elementary functional equation. I show just one. Find a function f, this is elementary, such that f of x, let's say x plus 1. This is for secondary school. It's a nice problem, so it's not easy to solve. I challenge you to solve it, and we can discuss in the break. So backing to our functional equation, our high level functional equation. So this is for students of 13, 14 years old in secondary school in Romania. And I have this example. We take, instead of AB, this interval, we have this function defined in this way. It is discontinuous, so it doesn't fulfill the previous assumptions, and I go to show you this. So it is not continuous. It is f of 0 is not 0, f of 1 is not 1, so neither A neither B is fulfilled, and moreover it is not strictly increasing because it's decreasing. So however we have that it has a unique fixed point 2/5. It is a Picard operator. This means this conclusion holds, without any of the previous assumptions. So the idea is that the assumptions here were too strong. So what I tried to tell you yesterday is that we have a look on a paper, on some arguments. So at that moment, I contemplated this definition, this example, because this was the main assumption for solving the equation by Malenica, by this mathematician. So I realized these are too strong, so we can weaken these assumptions. And here is another example. Actually, this is an almost contraction, as I presented you yesterday, in the sense, but it's an almost contraction having unique fixed points. The second example, it's an example of a contraction. The same, no one of the assumptions before on F are satisfied, because we have here two fixed points, and it is not continuous, it is increasing, let's say, but is not strictly increasing. And as I presented yesterday, Picard operator means a unique fixed points and the convergence of iterates, and weakly Picard means more than one fixed point, and Picard iteration converges to one fixed point. One more example is this one. I presented yesterday the identity map. It's also such a mapping satisfying the conclusion in the previous example by Malenica, and this is also a weakly Picard operator, and the set of fixed points is the whole interval 0, 1. So here it's an error in my text file. In this paper, we proved that almost contractions are in general not continuous, but if we have almost contraction, then it is continuous at any fixed point. So we can say this way, if we have a point B in which is a fixed point of t, then t is continuous at B, but in general t is not continuous. So this is the property of almost contraction. As I insisted yesterday, Banach contractions are continuous. So almost contractions have more than one fixed point, are not continuous in general, and they preserve the other conclusion in Banach's fixed point theorem. Well, to solve this functional equation, I write here, again to have here, to solve our functional equation, we need some prerequisite, because you know what I said about including, so gx, gfx equal capital Fx. This is our functional equation. To solve it, we need some knowledge about series, numerical series and series in the Banach space here, because I could work on the real line, but I prefer to work. Series are studied, I guess, in any university in the first year calculus course. I suppose people are are familiar with series. So in the case of a Banach space, we actually mimic the situation on the real line. No, nothing is really different. We have a series of positive terms, let's say, and we have this time n is positive, and we know what does it mean, the convergence of the series. We have criteria to establish if it is convergent or if it is divergent. Here we work in the Banach space Y and consider the partial sums. So Sn is the, you may know it's x1, x2, xn, and the series is convergent. Here it should be xn. Is convergent if Sn is convergent as a sequence. So this is the limit of Sn. If the limit of Sn is S, then we say that the sum of Xn is S. This is for a convergent series. And we also consider a sum of the partial sums. So we consider this sequence with double indices, Snk, which is defined in this way. Sn of 0 is Sn, and Snk is the sum, the partial sum of order k minus 1. We also consider this sequence Cnk, which is given by Snk over the combinatorial. Here are the symbol for the binomial coefficient. And in the theory of series, we say that the series S sum of Xn is C0 summable or C0 summable with the sum S if this sequence I put here, C is from C0, converges to S. In particular, if K is 0, we find the usual convergence of series. So this is a concept in summability of series. By the way, I mentioned yesterday an important name in fixed point theory, Billy Rhodes. I mentioned his classification of contractive condition. He was mainly working in this area. He was working in summability of series. And from summability of series, he came across with fixed points. Because I'll speak maybe more, but today I'll speak a little bit about Mann iteration. He realized that Mann iteration, in how it is defined, is defined through a summation rule. So he came across with fixed point theory, and he moved to fixed point theory for the rest of his career, and he did very nice things. As I mentioned yesterday, he did this nice classification of contraction conditions, and he was before a specialist in summation of series. So we know what is a convergence for series, but we also know what is means for a series to be C0 summable. This means that our series can be convergent, but can be divergent, but C0 summable. So these are the two variants. So we can work even with divergent series, but they are summable in this sense. There was a very extensive literature about the summability of series, and there are many kinds of summability. I just mentioned here this one, tuplets summable. This is also related to matrices, and there is also another concept. I'll give you the presentation, the file with my presentations, to can read more about this. I do not insist on these facts. So if you are interested, these are about tuplet summability. Again, we have a series. Normally it is not convergent, and then we consider an infinite matrix of real numbers. We construct this family of series, and which are assumed to be convergent with this sum, and in that case we say that the series xn, sum of xn, which is not convergent, is tuplets summable or T summable with the sum S hat. So this is a second kind of, this is the way Professor Rhodes were led to see that Mann iterations are related to the summation of series. And there is a third type of summation, is the Abel summation method, and you see the definition. So in that case we have a series. It is summable by Abel's method, or A summable with the sum S. If this series, we insert a t to the power n with t in an interval including -1, 1, if there exists this limit when t tends to 1 increasing. Okay. These are three types of summability, and if someone wants to see more, I was reading before taking the PhD topic in fixed point theory, I was interested in the convergence of series, and I just want to show you, do you know for this series the ratio criterion of convergence? Some of you, did you study this? We have this, if limit of xn plus 1 is k, then if k is less than 1, positive of course, then series is convergent. If k greater than 1, the series diverges, and if k equal 1, we cannot decide. Did you study this? Yes or no? Yes, okay. So I just want to tell you one of my results is not related to, but I used in fixed point theory. I have this limit form can be written under this form. Less than 1, and one of my papers, I was rather young at the time, I improved this criterion in this way, xn here, sorry. I improved this where Vn it's a convergent series. And this is, if a series satisfies this, then it converges, and this is, of course, a weaker form of this condition. So I improve this by putting here a term of a convergent series. So just in passing, I wanted to mention this. But we come back to solve this functional equation. So as you can see, I mentioned at the beginning, to consider an application of a fixed point result is not easy. So we have to build the entire prerequisite, what is needed to present this application. You can imagine if you include this in a paper with a fixed point theorem, a lot of material we have to include. So this is why we should be reasonable. So here are some results about the regular metrics, infinite regular metrics. I don't insist, and about the convergence of the series in a Banach space, because I want to move. Here is another theorem about the convergence of series in Banach spaces, and keep in mind that infinite regular matrix is directly related to Mann iteration, to Krasnoselsky Mann iteration. I'll speak on this later. And these are constructed by using a particular infinite regular matrix, any such iterative sequence. So coming back to our functional equation, this one, how we can solve it? It is not easy to anticipate how we can solve it. So we actually start from, I put here a general result. I mentioned yesterday, a normals contraction is a weakly Picard operator. So the result is given for weakly Picard operators, but in particular it is valid for almost contraction. So we consider F a weakly Picard operator, and the next small x in capital X arbitrary. By the definition of the weakly Picard operator, for any x, we know what does it mean, a weakly Picard operator. For any x, Fn x goes to, I said, a B, which is a fixed point of F in this case. So all the time, this means that it's a weakly Picard operator. So we consider this series. Look at the functional equation. F is in the right-hand side, and F is in the left-hand side here. So by considering this series, we can find sufficient conditions to ensure the existence of the solution for our functional equation by considering the convergence of this series or some summability means. So here it's the main result. I'll try to make it clear. We have, in general, weakly Picard operators. And we work in a complete metric space. Y is an arbitrary real Banach space. F, this one is a given weakly Picard operator, and F, capital F, is a given mapping. No special assumptions are needed for capital F. And we only suppose that capital F is continuous at B for any B, a fixed point of this map F. Then we have these four conclusions. First, in the case our series, our previous series, if it is, we can see how you call, we call alternate series. Do you call alternate? Because the sign changes. We call alternating series. This alternating series, if it is convergent, then its sum, let's say G, it's a solution of this functional equation. Moreover, if this f, small f and capital F are continuous functions, continuous mappings, and the series is uniformly convergent, then the solution is continuous. So it's very important. We have here, in fact, the solution exists, first part, and the solution is continuous, second part. So we can ensure the existence of a solution for this functional equation, and we can ensure a continuous solution. So the others are the three types of summability. So the series, in case our series is not convergent, but it is T-summable with this matrix K, T, which is a regular matrix. I don't insist on this concept. So we have the, I did not include it here, some assumptions on this matrix T. Then the sum of this series, the sum G, is a solution of the functional equation. Of course, it will be not continuous for sure. If we have Cesaro summable series, then again the sum of this series is a solution of the functional equation. And of course, in the case of the Abel summability, we have again the same conclusion. So this is what we can say about this functional equation. Look, the main tool here, the main tool was the fact that our map F was a weakly Picard operator, was a almost contraction or on another kind of contractive mappings which ensure that we have weakly Picard operator. In particular, of course, it can be a Picard operator, and this is one application of our result, our results about almost contractions in the class of functional equations. Okay, as I insisted yesterday, I pretend this is a new result, the preview theorem. This is a new result, but I pretend. So to complete my approach, I should prove that this is really effective generalization. So keep in mind, this is important. Believe me, I've seen a lot of papers. This is a generalization of this result. I don't believe this. I don't believe if you do not show concretely that indeed there is a mathematical object that fits this new result and does not fit the other one. So this is the supreme proof that your result is new. Your result is a generalization, is above the existing one. And this is a simple example. I have actually two. So we consider, okay, examples should be simple, believe me. Examples should be as simple as possible, but just to prove our assertions. It happened to me many years ago. I'm remembering always smiling. I was very young. I attended a conference. And at that time, I was working on Newton-type methods. I applied fixed point theorems to prove the convergence of Newton type methods. And the results were quite nice, quite general. And I had an example. Newton method, as you may remember, ask for continuous second derivative. This is an important assumption. But I proved the convergence just assuming the continuity of the first derivative and some other properties of the first derivative. And I gave an example, I do remember, very nice example, of a function which was not twice differentiable, it fulfilled, and the example was nice, and after I presented my talk, one colleague of Professor Rus, my advisor, very kind person otherwise, Professor Mikula, maybe you didn't know. He was alive, I guess. No, he was not. He died rather young. No, Mikula, not Rus, is alive, but his colleague of department. He asked, he said, Vasile, but this is a very simple example. Could you give a more complex? And Professor Rus exploded. Why? We need just a simple example. It's as simple as possible, just to prove our assertion. But he said, okay, I would like an example, this professor, Mikula said, I would like an example in maybe differential equations, something very complicated. And Professor Rus, and I follow him totally in this respect, said no, we need a simple example. So this is a simple example. Look, we have the unit interval with usual norm. We take f small and capital F in this way. So f is x over 2 for x01, and f1 is 1 over 3. It's not continuous. Fx is also, again, not continuous mapping, not continuous function, and it is easy to see that f is a Picard operator. It has a single fixed point, and we have this. We can compute fn of x, and then fn of 1, and we can see that for x1 is our b, in that case, we have this result. So the first condition is satisfied. So this is a Picard operator. So in that case, our b is 0, and we can see that f, our capital F, is continuous at 0. So this assumption in our theorem is also fulfilled. And moreover, this series, in that case, if we compute all, is this series which we can compute always. So our function, the unique discontinuous function is the solution, because we have some extra terms here. So our function will be this. G of x is x over 3, and g of 1 is 2 over 9. So it's a discontinuous solution of our functional equation. Why is discontinuous? Because this series is not uniformly convergent. So this is one reason. This is one example, simple example. So what does it mean? It means that this conclusion 1 is, and also f is not continuous. Sorry, so there are two reasons.
It has fixed point 0.
Yes, but the point is that also f is not continuous, because in we have these two conditions not satisfied. F should be continuous on the entire entire set, and this is not, so the series is not uniformly. So this is why our solution is not continuous. Then another example similar to that, but f is different. So here we have the same. We have convergence and we can see our series, this series does not converge for x equal 1. So we cannot apply the first conclusion in our theorem, but we are able to show that for x equal 1, this series is summable, and its sum is g of 1 over 2. So in this case, g given by 0 for all x in 0, 1, and g of 1, 1 over 2, then g is the unique discontinuous solution of the functional equation 1. This is our functional equation. So, what I suggest here is to consider other type of functional equation. I suggest you, it's an important topic. So this is one type of functional equations. There are many. This one. So there are many. So study, this is my suggestion, study with the same tools other types of functional equations. To my best knowledge, there are not results regarding the solution of such functional equations using fixed point tools of this kind. So I guess this would be a very interesting topic to work on. Also, I would be interested if someone, here the two examples, f is a Picard operator. This means the set of fixed points of f is only one point, so B. My challenge is to find example when f is weakly Picard operator. I have given in the talk yesterday some examples, and I guess it is possible to construct. I did not construct an example for this kind of mappings, but if we go back to our convergence theorem, so we see that normally we can work without any difference. So we have f, which is a weakly Picard operator. This means fix of f has two fixed points or more, and then for each fixed point we have this. Then we can have one conclusion, 1 or item 2 or item 3 or item 4. This is mainly what I wanted to show you about applications to functional equations of the theory of Picard operators and theory of weakly Picard operators. This means applications of fixed point to this kind of functional equation. Look, other types are suggested here. This equation, which is called Steinhaus, after the name of a mathematician, I didn't mention here the paper by Steinhaus. It is old. This should be another kind of equation. If you remember, so our equation was this one.